day, students. I am Dr. Monika Khetarpal, Associate Professor of Physics, Government Dungar College, Bikaner. In my lecture series of MSc Previous Physics, today I am going to deliver a lecture on Lagrange equation from D'Alembert principle. In my previous lecture, I have derived D'Alembert principle. What is the use of D'Alembert principle? Constraints introduce two problems. First problem is that coordinates are no longer independent. They are connected by equation of constraints. Second problem is that force of constraints are not considered. We have to remove these two problems. The problem of force of constraints is removed in D'Alembert principle. Here we have formulated our mathematical description in a way that force of constraints do not appear in the picture. We have assumed that work done, which is actually the virtual work done, because we are considering infinitesimal displacement. Virtual work done by a system is assumed to be zero. Hence, force of constraints do not appear in the picture. Now we have to remove another problem, which is of independent coordinates. For this problem, we are transforming our coordinates to a new set of coordinates, which are termed as generalized coordinates. These generalized coordinates are independent coordinates. That means we are transforming the position vector r into q. For this purpose, I am writing r as a function of generalized coordinate. We are choosing n generalized coordinate and they are denoted as q1, q2 up till q1. R is a function of n generalized coordinates and time. Now I am deriving velocity of ith particle. Velocity of ith particle is dri upon dt. Hence differentiating this expression, differentiating in terms of partial derivatives, I get first n terms from generalized coordinates and the last term is from time dependence. So velocity of the particle, ith particle, is del Ri upon del Qj, Qj dot, I have summed over all the n particles, plus del Ri upon del T. This is the velocity of ith particle. Now I am finding the infinitesimal displacement, as infinitesimal displacement is represented by delta Ri. This is not the actual displacement. Actual displacement is represented as dri. This is infinitesimal virtual displacement, which is represented by the letter del. Del Ri can be obtained from the functional dependence of Ri. Del Ri can be expressed as del Ri upon del Qj, summed over all n particles, plus del Ri upon del T. What does the del T means? This del T means virtual time. As virtual time has no physical significance, so del T is 0. Hence putting del T to be 0, we are left with del Ri equal to partial derivative of Ri with respect to Qj del Qj. Now to derive the Lagrangian equation, I am using D'Alembert principle. The D'Alembert principle is Fi minus Pi naught dot delta Ri. I have already derived the value of del Ri expressed by equation 2. And substituting the value of del Ri, here I am having two terms. I will find the value of these two terms separately. and then put them together to form the total value. First, I will find the value of first term. Here the first term is Fi dot partial derivative of Ri with respect to Qj del Qj. Fi del Ri upon del Qj. This is expressed as capital Qj. This capital Qj, it is termed as generalized force, as it has the dimensions of force. So we have got our first term to be equal to capital Qj del Qj. Now I will derive my second term. This second term includes the derivative of linear momentum. Linear momentum Pi, as we know, is mv. mv means miri dot. Here I have Pi dot, so we will have term miri double dot. Other terms being the same, partial derivative of Ri with respect to Qj del Qj. I can express this term as total derivative with respect to T mi Ri dot partial derivative of Ri with respect to Qj minus mi Ri dot d by dt del Ri upon del Qj. Here Ri dot means velocity, so I have substituted Ri dot to be Vi. Here also I have substituted Ri dot to be Vi. Now in this second term, to make it more easier, I am finding the values of these underlined terms. I have already derived the velocity of ith particle, which is expressed by the equation. First, I have written it again for the convenience. Now, to find the value, I am partially differentiating it with respect to Qj dot. So, differentiating with respect to Qj dot, here there is no Qj dot, hence its differential will be 0. So, we are left with the first term, and differentiating it with respect to Qj dot, I will get del Ri upon del Qj. So I have find the value of this term, which is del Ri by del Qj, to be equal to del Vi upon del Qj dot. Now another underlined term is d by dt del Ri upon del Qj. This can be easily seen to be equal to del Vi upon del Qj. So putting the value of these two underlined terms, I got the expression. To simplify this expression, what I am doing, here is a differential with respect to Qj dot. I have taken it del by del Qj dot outside, and since we have Vi here and partial derivative is with Vi, so I am putting it summation I half mi Vi square. This will form the term. I have taken summation of I inside, so outside there is only summation of j. Similarly, in this term, I have taken summation of I. As we know that total kinetic energy of n particle system is capital T, and it is equal to summation I half mi Vi square. So we get d by dt del T upon del Qj dot minus del T upon del Qj summation over j del Qj. I got the two terms of my expression. Combining these two terms, I got my expression to be in this form. Because constraints are holonomic and we have transformed our dependent coordinates to a new set of coordinates which are independent, they are generalized coordinates and they are Qj. Hence, coefficient of del Qj, they are independent of each other. So we can substitute the coefficient of del Qj separately to be 0. So what we are doing here, we are taking the coefficient of del Qj to be equal to 0. So we get the equation d by dt del T upon del Qj dot minus del T upon del Qj equal to capital Qj. This is termed as general form of Lagrangian equation. Here, what is capital Qj? Capital Qj is generalized force. Capital T is kinetic energy of the system and particle system. Qj is generalized coordinate. Qj dot is differential of Qj with respect to T. Since there are n generalized coordinates, J has a value from 1 to n. So there will be n such equations. We have differential, double differential here. So this is a second order differential equation. So depending upon the number of generalized coordinates, Lagrangian equations will be there. If there are n generalized coordinates, we will have n second order Lagrangian expressions. This is the general form of Lagrangian equation. In my next lecture, I will modify, or we can say we can extend this general form of Lagrangian equation to a conservative system and to a non-conservative system. This is a very important expression in classical mechanics. Thank you students for watching.